In the previous lecture, we had introduced the idea of a density matrix. The point that we tried to make is that in most cases that we look at in a physical system, the physical system is almost never an isolated system. That's because it's always a part of a bigger system and it interacts with its environment, and so as a result the problem is that we have to make measurements generally on an ensemble, and the other problem is that we could have a collection of different systems in the same ensemble, and when we make a measurement it is not necessary that we are picking up the same state all the time. In order to take care of these things, we bring in the concept of a density matrix, and as we'll see later that the entire quantum mechanics can be restated in the language of density matrix, which will be the more appropriate situation for talking about systems which are either parts of a bigger system or are members of an ensemble. So we had defined our density operator yesterday, and so let us look at first we will spend some time on the density operator for the pure system, where the system is described by a state vector. So let's look at, supposing I have a system psi, system with a state vector psi, then the corresponding density matrix or density operator is simply given by psi psi. Suppose I have in this situation, supposing in the Hilbert space to which the psi belongs, supposing this is the basis. Now if this is the basis, let us look at what is the expectation value of an operator A. We know that this is simply given by psi, A psi, and if we now express the state psi as a linear combination of these basis states, what we get is sum over I, sum over j, Ci star, Cj, and the matrix elements of Ei, A, Ej. Where this Cj, for instance, is the basis state scalar product with psi, and obviously your complex conjugate of that, which is Ci star, will be psi with Ei. Now with this, let us look at how much is the expectation value of A. So the expectation value of A, we can rewrite this expression by plugging in these two things, and what we get is sum over I and j. So we have got psi Ei, Ej psi, and of course the matrix element which is Ei, A, Ej. Now since these are scalars, I can rewrite them by interchanging their orders and write it as Ej psi, psi Ei. So this is equal to, so expectation value of A is given by sum over I and j. So you notice this is Ej psi, psi Ei, and of course the matrix elements of A within the states I and j, which I simply write it as this. Now this, you notice, is nothing but my density matrix rho. So therefore this expression is sum over I and j, Ej, rho, Ei, and this was Ei, A, Ej. Now what I notice here is that this cat Ei and bra Ei are together and nowhere else the summation over I appears. So therefore the summation over I can be shifted there, and you notice that if you take the sum over I of this quantity, that is nothing but the identity operator because of completeness. So as a result, this is given by sum over j of Ej rho A Ej, but sum of the diagonal elements of diagonal matrix elements of an operator is nothing but the trace of that operator. So this is trace of rho A. So therefore, if you know the density matrix, we have proved it at least for the pure states case. We will later on see that this is a relationship which is valid even for the general case that we will be talking about. So this is what it is. Now taking the special case of A as an identity, if you take A as an identity, then you notice you get trace of rho is equal to 1. Now this we will see is a property of density matrix which is always valid irrespective of whether the state is a pure state or a mixed state. Mixed state we have not yet defined, but we will do that. Look at the slides here, which sort of gives you some of the properties that we have derived so far for the pure states. We had last time defined the density matrix for an ensemble or a mixed states as being given by sum over I pi. Pi is the probability with which the state psi I appears in an ensemble, and so therefore the general definition of a density operator is sum over I the probability I times psi I, and for a pure states this obviously is simply psi, and the expectation value of an operator we have just now shown it to be given like this. So with that, let us go over now to the matrix representation of a density matrix. So obviously if I have a basis, let us say EIs or whatever, now I define the mnth matrix elements as given by the matrix element of rho in the states Mn. So recall that rho is my psi. Now so the diagonal matrix elements are rho, let us say is Em psi, then psi Em, so which is nothing but absolute value of Em psi square. Now, but however you recall that this was nothing but the definition of my probability in the Born interpretation of quantum mechanics. So therefore this is nothing but Am or Cm as we wrote it, Cm absolute square. So this is the Born probability of getting a state n when a measurement is made. Now that leaves us with off diagonal terms of the matrix elements of the density operator. So these off diagonal terms, if you look at a typical off diagonal term, suppose I say m is not equal to n, then let us write Cm as equal to mod Cm e to the power I phi m. We need Cn star which is there, so this is equal to Cn mod e to the power minus I phi m. So therefore my mnth matrix element is Em psi En. So this is simply Cm Cn star, and that is equal to mod Cm mod Cn e to the power I phi m minus phi n. So you notice that the off diagonal matrix elements, these depend on the relative phases between the states m and n, and these result in the interference term. So the off diagonal matrix elements for m not equal to n, these give rise to the interference term. So just give you some examples of a density matrix written in for a single qubit system. So let us look at a state, a normalized state, which is given by psi equal to, suppose I write 1 over square root of 2 0 minus I by square root of 2 1. This is a normalized pure state. Now according to our column vector representation, this is simply given by 1 over square root of 2, 1 and minus I. So therefore the density matrix rho is simply this product, which is a matrix direct product, which is equal to 1 over 2, and you can easily multiply the corresponding matrices, namely 1 minus I with the row vector 1 plus I, and that gives you 1 over 2, 1 I minus I 1. Notice one thing, that the trace as expected is 1 by 2 plus 1 by 2, which is equal to 1. The another point to notice is the rho is Hermitian, and this is again we will see is a property of a density matrix, the hermiticity of rho. Let us look at these slides. So the point is this, that if you are looking at the density matrix rho, I can of course write it like this as I have shown it to you earlier, and the diagonal elements of the density matrix gives you the Born probability of getting a state. Now the another point to notice, these diagonal elements being modulus Cn square, they are essentially non-negative quantities. So therefore the density operator is a positive operator. This is another general property of the density operator. And the another point that we would like to make is that the density operator satisfies what is known as the Liouville equation. I am showing it simply in the slide. It is a fairly straightforward algebra. You should do it. Looking at the slide, see, since psi is a state, so I have I h cross d psi by dt is Hamiltonian acting on psi. Taking the Hermitian conjugate of this, I get minus I h cross d by dt of bra psi is bra psi acted from the right with the Hamiltonian h, and if you calculate what is I h cross of the density matrix rho, this is simply done by a chain rule differentiation, and you will find it is commutator of the Hamiltonian with rho itself. One point to notice, that it does not satisfy Heisenberg equation of motion, even though rho is an operator. And the main reason is this, that rho is an operator in the sense that it has the mathematical structure of an operator. But Heisenberg equation of motions, which essentially said that I h cross dA by dt is commutator of A with the Hamiltonian, is valid for the case where A is an operator representing a physical observable. Now rho, though it has the mathematical structure of an operator, it does not represent a physical observable, and the equation that it satisfies is the Liouville's equation. So the Schrodinger equation in my for the state is leads to the Liouville equation for the density operator. So with this, let us generalize to the case of an ensemble. So in which case my rho is sum over I pi psi psi. Look at the slide. Now clearly rho is Hermitian. and it takes a very trivial exercise to show that trace of rho is equal to 1, which simply comes by taking the trace of both sides and using the fact that total probability sum over I pi is equal to 1. Now one point is that for a pure state, rho square is equal to rho. That's fairly straightforward. You have psi, ket, bracket is the structure, and if you write rho square, then of course one psi and its bra and its ket will come together, giving me 1. So therefore trace of rho square is same as trace of rho, and that's equal to 1, of course. Now since it's a positive operator, its eigenvalues are non-negative. Now this property that rho is equal to rho square is however not valid for the mixed state density matrix. And there's a matter of very simple way to look at it, that the density matrix is actually sum over I pi psi. So the point to note is a mixed state does not have a state vector, but it is described by a density matrix. Just to give you a general idea, let us look at the following. Suppose I have an ensemble which has let us say 50% in state 0, and let us say another 50% in state 0 plus 1 by root 2. Now I can individually calculate the density matrices for each one of them and then add them with the probabilities. So therefore my rho would be the probability half times the density matrix corresponding to this, which is 0 0, plus the second state's probability, which is half, this times 0 plus 1 by root 2 multiplied with 0 plus 1 by root 2. Then you can open it up and write this. You notice there is a 1 over square root of 2, 1 over square root of 2, so there is a 1 over 4 there. So I get 3 by 4 0 0 plus 1 by 4 1 1. There are cross terms here, and these cross terms are 1 by 4 1 0 plus 1 by 4 0 1. So if I now look at a matrix representation of this is clearly 3 by 4, 1 by 4 and 1 by 4 here and 1 by 4 there. Look, clearly the trace is still equal to 1. There are off diagonal matrix elements here. So therefore this is a partially mixed state. Why partial? I will come to. See, it's a partially mixed state because the off diagonal matrix elements are there, but they are not that big. For instance, if you take an ensemble which has, let us say, 75% in state 0 and 25% in state 1. The corresponding density matrix would be a diagonal matrix 3 by 4, 1 by 4, 0 0. Notice we have reduced the amount of the strength of the off diagonal elements, so, and have made it 0. So this is a completely mixed state. Now the case where it is still diagonal, but the diagonal elements are all of equal strength, that's called a maximally mixed situation. So this is what the density matrix for the mixed state is about. Having done that, let us look at a representation of the density matrix. There is another point before I go over to that I would like to make, that suppose you have a situation where you find that rho 1 is equal to rho 2. The question is that does it imply the same state? Well, I have said that there is no concept of a state, but does it imply the same mixture? The answer is no. Rho 1 equal to rho 2 does not necessarily imply that the two ensembles are the same. This is an important point to note, because for a pure system, psi 1 equal to psi 2 of course implied that the states are indistinguishable. And you can see it why. Supposing I consider a case where 50% is in state 0 and 50% is in state 1. Now clearly this is a state in which I have got 1 by 2, 1 by 2 as the density matrix. Now on the other hand, supposing I define a state in which ensemble in which 50% in state 0 plus 1 by root 2 and another 50% in 0 minus 1 by root 2. You can calculate the density matrix by the definition I have given, and you will find I still get the same density matrix. Note again that we are saying that for an ensemble, the concept of a state is not there. So an ensemble is given by a density matrix, and the postulates which we had corresponding to the state vectors, the postulates of quantum mechanics, can be replaced by the corresponding postulates for the density matrix. Now you can immediately see what those postulates should be. So you say that an ensemble is described by means of a density matrix which lies in a Hilbert space, in which the state vectors corresponding to the component states are there. The other thing is that the Schrodinger equation which every state satisfied is replaced by the Liouville's equation for the density matrix. And so therefore this is some of the things that we need to talk about. Just before we close this section, let me give you an example from physics. Suppose I look at a coherent superposition of state plus k and minus. So let me take a state psi which is equal to 1 over square root of 2 plus k plus minus k. That is equal momentum, equal and opposite momentum added with the same. So you can calculate what is the density matrix corresponding to this and find out what is the corresponding wave function. The wave function, as you know, is the projection of these states onto the position space, that is the real space, and you can calculate the probability or of the density at point x. So which is given by, remember it should be corresponding to the density operator rho and of course the position operator xx. For those of you who are not familiar with this part of physics, can skip next couple of minutes, but this is given by x by definition of the trace x, and you can simply plug these numbers in, psi, rho, psi, calculate this and show that this quantity is equal to 1 plus cosine of 2kx, which obviously shows fringes. That's because the intensity keeps on varying sinusoidally. Now if you took an incoherent superposition, that is, instead of doing this, So we take for example a density matrix which is given by, remember that when we have incoherent superposition I cannot define a state, so this is 1 over 2 kk plus minus k minus k. Repeat the above calculation with this and you can find that px will turn out to be equal to 1 and there are no fringes here. So what we have done today is to define the density matrix corresponding to both pure state and an ensemble of pure states which are called mixed states, and stated that when we look at systems which are collection of different types of systems, different states, an ensemble of different states, what we need to do, replacing the state vectors with the statements about the density matrix. We have related the expectation value of an operator to the trace of the operator multiplied with the density matrix. We have also pointed out the interpretation of both the diagonal and the off diagonal components of the density matrix, and we have seen that the density matrix is not unique in the sense two different ensembles could have the same density matrix. In the next lecture we will be looking at the relationship that the density matrix has for the single qubit systems with the block sphere which we have discussed earlier.